person in at this conference to say happy birthday to Leonid Andreevich, who is not in the room. Oh, I'm sorry. Well hidden. I'm sorry. So happy birthday. And now to go to the talk as such. Well, just as this meeting is a follow-up of the original program organized in 2008, this talk can also be considered as a follow-up of the last talk I have given at the conference in December 2008. The title 4 years ago was Simple Proofs of Simple Results in Multiparticle Localization Theory. Now there's more than that. So let's start with it. First thing to say, I believe, is sorry, my vocal cords are not in good shape today. Is to avoid any misunderstanding, any confusion, I have to say that the way physicists treat many-body problem in a disordered medium and the way it has been done so far in the mathematical world is different. Physically, what is, of course, much more relevant is a system of positive density. Again, physically, you have to take a finite volume, well, macroscopically or macroscopically large, but finite, with some positive density rho here. The configuration space, at least for a mathematician, may be a lattice or a more general graph or quantum graph or Euclidean space. And of course, at the origin of this multi-particle approach to localization was what we have known since many years already, but under a simplifying assumption of absence or negligibility of interaction, one can isolate one particle and study its spreading or non-spreading in the space. Okay, so if we isolate one particle, we can consider the eigenvalue equation in the entire configuration space, which may be infinite, or in a large or small part or thereof. It makes sense. The situation is similar for a fixed finite number of particles. Even in the infinite space, you can still have a well-defined eigenvalue equation for example, 10 billion particles in an infinite universe. But it all changes radically if you take positive density and infinite space. Then any notion of eigenvalue equation, at least for a mathematician, is completely lost. Everything you'd need, even eigenvalue, would be a desperately divergent series. Well, of course, there are things you can do. You can do quantum statistical mechanics, but it's a different story. Now, like I said, only finite number of particles can be considered so far rigorously. Or if you take a large volume, you stumble with the same difficulty that appears in an infinite volume. You can treat a certain number of particles, but the price for going from, for example, 100 to 101 particle is to impose stronger and stronger restrictions on the parameters of the system. For example, you may have to require stronger disorder, yet stronger and stronger, or you have to take your energy closer and closer and yet closer to the spectral edges, one edge or edges. And of course, quite rapidly, this parameter zone, where rigorous analysis can be carried out, is degrading. That has been the main problem so far. One question has been asked to John Imbri, I believe, what is the main difference between complexity of the configuration space, like tree, for example, and the configuration space for many body problem. Well, apparently there are many different answers. One of the striking distinctions to my mind is a complete lack, well, almost complete lack of what's called independence and distance, which is normal thing, for example, in one particle theory with the IID or short-range correlate potential. And independence and distance in a already two-particle configuration space is more rare than free lunches. Now, the first two approaches are reported here in this institute in 2008. One based on the multi-particle adaptation of the multi-scale analysis in our works with Yuri Sukhov, later continued in a larger team, and by multi-particle adaptation of fractional moment method by Eisenman and Marzel. Both used induction on number of particles. So starting with some information about single particle theory, you can make one step, then modulo some technical conditions, you can make another, and mathematically speaking, you can do any number of steps. As I explained, that requires stronger and stronger restrictions on the parameters of one particle system. Okay, so two main topics. I prepared, more slides that I would be able to discuss today. But the two main topics of this talk are two new tools, recent new tools, which appeared here. The first is elaboration of a sort of analog, not quite direct, but analog of the well-known Simon-Wolf method, which derives, the Simon-Wolf method derives spectral localization from fixed energy analysis. And no such statement has been known so far for multi-particle systems, even for two particles. So actually, one can prove it, and it is very, very simple. The other topic is a new tunneling bound. I hope to have time for a short discussion of it. It's actually only a part of the multi-particle localization analysis, but it radically changes the structure of the induction on particles, and I will comment on it later. So before going to these main topics, just under different circumstances, I would be glad to comment on each of the new results appeared since the original program, Mathematics and Physics of Anderson Localization. But as you can see, yes, in light blue are indicated the collaborators and the names of two PhD students, of whom Almute de Monvel and myself are advisors. So there is a whole lot of different models, all investigated by multi-particle, multi-scale analysis, for which, in the setting which I briefly explained, one can prove Anderson localization for any fixed number of particles, but let me say it for n+1 time, the physical range of parameters required, for example, for 100 or 1,000 particles is more or less ridiculous. So this is why, for the lack of better word, I would say that this is a few particle theory, nothing more, nothing less. More or less equivalently, one can put it in the following way. Given a number of particles, you could for 2, 3, 7, and given some parameters like disorder or proximity to spectral age, you can say in how large volume you can prove of a large but finite volume, you can prove Anderson localization. Okay. Now a few geometrical definitions for the rest. I will often call the finite volumes balls, because even in the most popular setting where we work with cubes in multi-scale analysis, they are still balls in Mach null. Well, actually, most of the time I will be speaking about discrete configuration space. For the purposes of drawings, I will be using Z, most often Z1 or Z2. And practically all I'm going to tell you is a general extended easily to any countable graph with polynomial or even slightly faster growth of balls. Now, the main property for the first part of the talk will be goodness of a box at fixed energy. And like I said, fixed energy analysis will be the most important assumption. We will assume that this property is satisfied by means of a preliminary fixed energy multiparticle analysis. That will be assumed. And the goal of the first part of the talk will be a derivation from the assumption, stronger manifestations of Anderson localization, namely spectral localization and dynamical localization. Okay, so to make it a bit more general, I will not impose any particular structure of this function h1. Just let's say that the matrix element of a green function in a ball of size, or let's say radius L, centered anywhere you want, from the center, between the center and the boundary, is small. That is a localization according to the smallness functional parameter h1. Well, most popular setting will be h1 negative exponent, and in that case, I will say that this box, or rather operator, local Hamiltonian in this box, is M non-singular. Sorry, non-singular. The same NS stands for non-singular. Should be here and here the same. Now, here is the Hamiltonian. It will not appear often on the subsequent slides. There is a kinetic energy given by whatever you want, for example, negative Laplacian, plus the sum of potential energies of all particles, plus interaction. Now, speaking of the proven results, I can tell you that now U is not necessarily short range. It may be first sub-exponentially decaying, that is, decaying with a fractional exponential rate. And one can still prove, at least for some range of this fractional exponent, prove exponential decay of green functions and ultimately eigenfunctions. For polynomially decaying interactions, well, there is no miracle. One can only prove so far polynomial, fast polynomial decay of green functions and finally eigenfunctions. Please don't ask me this question now, because it will take a long time to answer. Mathematically, I'd say there is some power. Okay, the disorder will be taken very, very nice, nothing like Bernoulli-Anderson, the nicest you may imagine. It can be actually relaxed to Hölder continuity in at least for some results for log Hölder continuity, but let's take it the nicest distribution you like. So here this interaction, again, the two-body structure is not necessary, isotropy is not necessary, but let's take it this simple form. Now, okay, what is the goal? Now, the first stage. We assume that this property, which I will be calling singularity bound in an interval, so in an entire interval I, for any fixed E in I, and for any center, of course, the singularity, that is lack insufficiency of decay of green functions at energy E, is unlikely. That is the assumption. And of course, you can take different functions, H2 here and H1, which I previously defined. Of course, in the framework of the multiscale analysis, you can never hope to get H2 exponential in L, only sub-exponential at best, or polynomial, which is sufficient for the purpose of the proof of localization. And the goal is to prove that with H1, which measures the smallness of green functions, for example, exponentially small in L, H1, and sufficiently fast decaying H2, this fixed energy assumption, the outcome which should be an outcome of the fixed energy analysis, is sufficient for the almost sure pure point spectrum and for non-spreading of wave packets. Okay, now the main ideas, mostly graphically. It all starts with a very nice observation made in '85 by Martinelli and Scopola, and later appeared in a number of different papers, most notably in Simon-Wolf's one. Like I said, it's a sort of generalization or extension of Simon-Wolf argument to multi-particle systems. Well, let's consider not just energy or disorder separately, but the product space. Then let me recall, the E singularity means that it is you don't have in this ball or in this box enough decay of green functions. It's a bad event. This happens for some, may happen for some energy and for some sample. So let's put in gray here the set of all pairs E omega for which the ball is bad. It is not E good. Okay, performing, as we assumed, fixed energy analysis, that is taking vertical sections of this set in the product space, you know that each section has a small probability. That is a small integral in omega. By Fubini, you know that the product measure of this set is small. Now, again by Fubini, take a horizontal section. Then the set of energies, and again, for the lack of a better word, let's call it a singular set of energies or set of singular energies. This this orange set has to, well, it has a random measure, random Lebesgue measure, right? So this random Lebesgue measure has a small expectation due to Fubini theorem. Now we can turn it to our advantage and say that by Chebyshev, typically this measure has to be small because the expectation is small. So that was the starting point almost 20 years ago. Now let us assume, and this not as innocent assumption as it may appear, that not only this set script E is of typically of small measure, small Lebesgue measure, but it is concentrated around the spectrum. Well, actually, did I put it? Did I? Oh, okay. Here, just for reference, the first method I'm going to explain you is essentially a reformulation of a very nice paper by one particular result, technical result from a paper by Elgar, Taubenhahn, and Veselich. There is another method which I developed because this one works very well for fractional moment method and less so for multiscale analysis. Okay, so let's assume for the moment that the singular energies are indeed very close to the points of the spectrum. If we assume that, and in addition we assume that we have what I would call two-volume Wegener type estimate. That is the proximity of two spectra in two distinct balls. And now in the multi-particle setting, we are speaking about multi-particle balls. this proximity is unlikely. Then the overlap of this red singular set and this orange set, one is for Hamiltonian around X, another around Y in the multi-particle configuration space. This overlap is also unlikely because overlap happens only if the centers are too close, and the centers of the intervals are eigenvalues. It is not the usual Wegener type estimate because in multi-particle case, like I said, there is no independence and distance due to correlations in the potential, which is of the form, for example, V of x1 plus V of x2, already for two particles. So, but if we assume that these energies are close to the spectrum, to the respective spectrum, and we do have two-volume Wegener type estimate, then we achieved our goal. We derived from the results of the fixed energy analysis the statement that at two different loci, the green functions are both not sufficiently localized with small probability. It's much stronger. From that, using the machinery which in single particle case goes back to 1980s, you can easily derive the almost sure point spectrum. And the last step to perform is to derive also dynamical localization. So the first three items, and today I rather skip it. The first three items just summarize what I have explained with the illustration. And so far, I have been relying upon the method by Tautenhan, Elgar Tautenhan and Veselec. And the last remark is that in this method, the estimates on the green functions and ultimately eigenfunctions are only as good as probabilistic estimates of the first stage fixed energy localization analysis. With MSA, all you can dream of is sub-exponential, not better. But if the first stage has been performed by multi-particle FMM, then of course this works fine and gives you exponential decaying green functions and eigenfunctions. So this first part, the first three items, give a sort of universal derivation of stronger manifestation of Wagner-Anderson localization, namely decay of eigenfunctions through green functions, regardless of the nature of the techniques used to perform the fixed energy analysis. Whether it is FMM or MSA or whatever may appear in future, it doesn't matter. It is an implication. Okay, the derivation of the dynamical localization, strong dynamical localization, from the variable energy analysis, which I have just explained, has been known for single particle systems for quite a while. Well, I would say that methodologically it goes back to the work by Del Rio, Zhytomyrsky, Last, and Simon, where the role of the so-called localization centers has been explained. Then it influenced the works by Germinet de Bièvre, then Domanic-Stolman, and probably that is the last step made by Germinet and Klein, who simplified it enormously. Basically, the main argument is a half-page calculation, and all you have to know is the Bessel inequality, provided that when you work in an infinite space, you have a controllable, polynomially bounded eigenfunction expansion. However, if you work in a finite volume, no matter how large, 10 billion parsecs, you always have, for an operator with complete resolvent, an orthonormal basis. And that's all you need for Bessel inequality. So again, I have prepared a slide to explain this, but it is well written already in the original paper by Germinet and Klein from 2001. and also in recent papers I put in archive. Now, so this is the statement a la Germain-Klein. Actually, it's just a finite volume version thereof. If we have two volume bound on singularity, that is absence or insufficiency of green functions decay into loci with smallness controlled by the function h, then for h good enough, you have also a decay of eigenfunction correlators, and therefore, if you take this function phi of your Hamiltonian like a complex exponential, you get the usual dynamical localization. So that now I have fulfilled the first step, and a few words about about the new factorization bound for multi-particle, multi-scale analysis. Well, probably it's better to start with pictures. So let's take the configuration space Z1. Here lives the first particle. Another replica of this space is where X2 lives. Along the mid diagonal is a band where the interaction, let's assume it finite range lives, and the balls or boxes we need for multi-scale analysis are squares here. Some of them overlap with the band where interaction is non-zero. Let's call them fully interactive, or you may call it also non-decomposable. And living outside of the band will be partially interactive, which makes sense if you have more than two particles. Here I would say it's non-interactive. But anyway, it is decomposable in this algebraic sense. That is, it's oh, sorry, it should be H, of course. H on the ball BM. So you have an algebraic decomposition for the Hamiltonian in a decomposable or PI, partially interactive box. Now, if you take two Fi boxes at sufficiently large distance, they have non-overlapping projections, and therefore they are independent. And you can proceed with them exactly the way you do in a normal single particle analysis, but in high dimension. The main difficulty, no matter how silly it may appear, comes from the PI boxes, especially when the number of particles is 3 or more, for reasons which I will not be able to explain today. But these are the reason for the most significant difficulties. Now, yeah, for partially interactive, decomposable. When the system is decomposed in 2 or 3 clusters, which are too far from each other to interact. But there are, of course, interactions. There may be interactions within each cluster. Now, to apply à la lettre, in a verbatim sense, the multi-scale analysis, you'd need factorization of events, of probability of events, like the box is bad, not enough decay of Green's functions here, and the box around the point y is bad, which is possible where they are independent, decomposable, but for partially interactive, it's much more difficult, because again there is strong dependence at any distance in the multi-particle space. Now, quite rapidly, let us make a quick analysis of the situations due to which a larger box at scale Lk+1, as usually in multi-scale analysis, is maybe bad. First, you may sit almost at a pole, at the pole or near the pole. It's a resonance, which you can rule out by Wegner estimate. You have to work, by the way, to prove it, but it's much simpler to prove for one box. Now, in the multiscalar analysis, you have to rule out the probability, the situations with high probability that 2 or more boxes are bad. And if, and this is a very big if, you can prove that the probability for 2 boxes to be simultaneously, that for the same omega and the same E bad, it is almost factorized modulo some innocent looking binomial factors. Then you're done, and you use the usual multiscale analysis. However, the way it has been done for partially interactive boxes, where there is a decomposition in the two clusters, was a sort of big concession. There was no factorization as such, and the only way to make the probability estimate you'd need small enough, you required more and more and more on the signal particle components of your system. That was a very big concession, and the growth of the typical parameters is exponential, which is why I told you that basically it's a few particles theory. 2, 3, 7, or 10 may be doable, but 100 you have to forget for it if you do some reasonable physics. Now, yeah, well, okay, let's skip it. It's just a completion of the multiscale analysis. Now let's see why and how can you prove the factorization of probability to have 2 distant multiparticle loci, both, not enough decay of green functions. Well, this is actually the hardest situation which you can show already for 3 particles. Let's say in one-dimensional space you have 2 particles from configuration X sitting here and here, and you have some balls around them, and another guy far away, so it is a decomposable system. Let's say we have another ball where the first particle sits near the first cluster from X, and 2 others near X3. If you have even more clusters, it's much simpler. Let's say it's even simpler. So it's basically the hardest case. If you look at it from the point of view of spectral theory, you see that the operator living in the Cartesian product of this interval, this one, and this one, is as strongly correlated to another Hamiltonian with projections, this, and this one. That is, virtually any value of the potential which affects the first Hamiltonian affects the other, and vice versa. It's as strong as you can imagine. How can you prove factorization in this case? Well, the idea, which I only have the time to outline, is the following. Decompose the potential into the sample mean for sample average and the fluctuation field. Then, if you freeze the fluctuations, your potential becomes actually a scalar operator. That is, in the full Hamiltonian, you have something which depends only upon the fluctuations, and you have 2 scalar random variables. One is due to the sample average in this set Q, which englobes these 3 intervals, and this is sort of complementary. So for 2 Hamiltonians, you have 2 random variables and something which is more or less constant. Now, the final calculation is the following. If we recall ourselves that singularity, not enough decay happens only around the eigenvalues, then the eigenvalues for one operator are given by some constant depending only upon the fluctuations in the first cube, plus 2 random variables psi q complementary. There is a similar form for the other eigenvalue from the other ball, where the only thing that really changes is M2, the number of particles sitting in the ball. And E prime, E double prime are fluctuation dependent or fluctuation measurable. Then, since the linear system with epsilon equals 0 has a non-zero determinant, then the set of solutions for the system of inequalities has a measure of order of epsilon squared. And actually, it is this power 2 which is responsible for the factorization required for the almost verbatim application of the multi-scale analysis in the multi-particle setting. So the rest, yeah, okay, that was the logical part of the talk. After that, there is a number of slides with the technical details. But let me summarize that. Did it appear here? Oh, no, okay, that's not. So let me just say it. So the two new steps, which I presented briefly today, were a multi-particle analog, although not quite direct, of Simon-Wolf argument to multi-particle systems, and also a way to approach the multi-particle, multi-scale analysis to the way it works and works fine for single particle theory. Although the local Hamiltonians, let me say it for the 10th time, local Hamiltonians, even for two particle systems, are correlated and strongly correlated at any distances. So I think that's it. Thank you for your attention.
At the end of the talk, you described sort of factorization or lack of tunneling, control and tunneling between, and but that was kind of like just a tool in order to prove complete the multi-scale analysis. But is it possible to actually think of that as a result that under certain circumstances, the wave function, say for a two-body system, is approximately a product of one localized over here and one over here?
Well, it's not a complete self-contained result in itself, but it solves a very painful technical problem which has been bothering me and my collaborators since the last program. So it's a radical improvement, and now the whole, like I said, the entire multi-particle induction in the number of particles, even for few particle systems, has to be rewritten completely. It's basically the hardest technical problem which we encountered so far. And there is a progress in this technical problem.
Does it allow to make estimates independent of n?
No, but thank you for the question. My feeling is that you can never, with this kind of arguments, especially with multi-scale analysis, maybe it's better with fractional moment, you can never dream of attaining in a box of size L or of L particles. However, I expect, it's just a guess, not completely unreasonable, but just a guess, that you can afford a small fraction, at least a small fractional power of L, which is still zero density. But to go further, I'm completely convinced I have to start with a much more accurate theory in the factorized space, Hilbert space, with no interaction, where the natural basis is given by the tensor products of the non-interacting electrons.
How is that will be related to these papers of Outschler and Daleiner on localization with interactions?
Okay. the serious, rigorous work, like I said, has to start with the eigenbasis for the operator without interaction. Okay?
So that's what they do. But then they have various statements that are, of course, not rigorous. How, which fraction of this does this resolve?
Well, in my understanding, and unfortunately I wasn't being able to talk as much as I would with physicists here, my feeling is that in these works, you take for granted that the initial state, which you start to perturb by an operator, is a function with particles which are very sparse, which have localization centers very sparse. Now, the perturbation analysis they do is for one particles. And what happens in a very high order of perturbation theory, when you, by your diagrams, you have two trees of diagrams get together, I don't know, because I'm not a physicist, and I'm not sure this question was addressed. Perhaps it was, and then I am terribly sorry. But my feeling was that there is not enough ground so far for a mathematical statement of any kind here, for very high orders of perturbation theory. However, I interpret their results as a local perturbation analysis for each particles separate from all the others.
Any other questions? Okay, let's thank the speaker again. Let us thank all the participants.